And now you will see what we covered, what we have started covering. One thing that I wanted to tell you, it's interesting, the book starts with Coulomb's law and solves a number of problems. Of course, what I decided to do is to start with Coulomb's law, introduce the divergence theorem, and then show that the two come together, both Gauss's law, Coulomb's law, through the divergence theorem. They all connect, they all get connected. And that is important. The book starts with Coulomb's law, solves problems, go to divergence, solves problems, and then goes to Gauss's law, which is fine. It's like a very expansive way of presenting the same thing. But I wanted for us, I present it all together because I want you to see that they're not separate things. So that's what I wanted to say, that I remind you here, what is the divergence theorem? All right, the divergence theorem says that if I have a vector, D, for now, let's assume it's any vector D, that the volume integral around a volume which I define, and you see the volume here, it is there. I define it, and this volume is enclosed by a closed surface. That's a condition. The surface of the volume is closed, obviously. And the surface is a vector. We talked about that. And the vector is always normal to the surface outwards, all right? Correct direction of the vector. The divergence theorem says that the volume integral of the divergence of D is identical to the closed surface integral of the D vector over the surface that encloses the volume. And if you apply that and you consider Gauss's theorem, that you can prove, but here, I mean, it's an extensive thing. So here we are going to take it as a theorem that the divergence of D equals to the charge that produces it at that point. So for example, what I meant to say is the following. This relationship that I have here, I show, it's a differential relationship. What does differential mean? It applies at one point. So at every point in space, this relation will apply accordingly. So if this relation here applies at a point P, at that point in space P, it happens that you have a charge Q, point charge Q, then this relation applies. Now, if I move to another point O, so in here there is a charge Q. If I move to another point, let me change it. Another point, say what? P, Q, S, S. Oh, that's surface. I don't want to. To another point, P prime, where there is no charge, no Q, then at that point, the correct relationship would have been divergence of D equals 0. All right. So practically, if I am to be complete here, I would say that these are the two relationships where here is where no point charge, no charge at that point. And here, charge Q. So wherever there is a point charge, the divergence of D at that point is Q. If there is a charge Q at that point. And if there is no charge at that point, the divergence of D is 0. That's what Gauss's law says. All right. So, and this is an important relationship. You need to remember it. Okay. Now, then what we have found is when we apply the divergence theorem to Gauss's law, and then, okay, so we define a volume V. And maybe you have only one point Q there. You see only plus Q at the center or at some point of this volume, the red charge that I have Q. And we apply the divergence theorem. Then we find that if the charge is that at that point where I have it, if the charge is at this point, O, and I apply the divergence theorem, I can find, and to the Gauss's law, I can find the divergence at any other point in the volume. And so the divergence at any other point in this volume is given by this relationship, like Q, which is that red Q, it's not another one, all right? Is that Q that generates D, it's only one Q, divided by 4 pi, and then the magnitude of what vector? Of vector R, which is the vector that connects O, the place where the Q is, to P, where I am observing D. And in fact, what I would like to show you here is that you can go from this part, look at the difference between this and this. What is the difference between the two? The difference is that I have replaced the unit vector by something else. So why do I do this? Because of the following. We know, we have seen that the point vector A sub r, we have defined it as, which is the director, the point vector along the r direction, along the direction of vector r, is vector r divided by the vector's magnitude. Do you remember that definition for the unit vector?
Yes, ma'am.
Okay, perfect. And as a matter of fact, what I will do here, I will write this like this. All right, so you understand is the unit vector along the capital R direction. So we replace this hat, A sub r hat, by this ratio here. We place that in here, and that's how we get with this relationship there, which is very useful, and you will see it in the example we are going to solve. What is this that we found? Coulomb's law. So practically, the divergence theorem allows us to go from Gauss's law to Coulomb's law. And let me also change the color in this. Okay, so that's what we have. And this is very useful, all right? So practically, either you start with a divergence, either you start with Coulomb's law, you come to the same result. However, I meant Gauss's law through divergence, or Coulomb's law, you come to the same result. However, I have to say one thing, and you will see it in some of the examples we have today, that starting with Coulomb's law, the one that I have here, to find the total field by many charges, or by a source, by a charge that has a density is distributed, all right, is going to be more difficult than if we were to start with Gauss's law, which is this one here, and then work would then apply to that the divergence theorem for that particular case we have. So you will see, in fact, you will see how we are going to do that in this example. And let me just change this so you can see it better. All right. Let's try to do that here. Do you have any questions about what we discussed before we go to the example? Okay, let's then try to solve this together. I have now two charges, one charge Q1, and I give you units here, so be careful When you solve problems where now we are getting into electric fields rather, you should always try to make sure you understand how to apply the units and apply them. So you have a charge Q1, which is 5 millicoulombs, and you have another charge Q2, which is 2 millicoulombs, and they're all separate. And I give the position of the two charges with the coordinates of the points where the charges are. So I have selected, to make it simple, Q1 to be on the XZ plane, you see Y equals 0, and Q2 to be on the YZ plane, so X equals 0. And then we want to find the total field at point O, which is the center of the coordinate system. So how do we do this? Okay, let me see here. So we're here, add a page. What I will do is the following for you. I will take this figure, all right, copy it, and then put it here, and then tell you the following. When you have two separate independent sources, so Q1 and Q2 are independent, all right? So I have defined them myself. So Q1 and Q2 are independent. When you have independent sources and you want to find the total field that is generated by the two sources, then we use what we call superposition theorem. Have you heard about this?
Yes.
All right, perfect. Superposition theorem, there are two conditions to apply superposition. What does superposition mean? It means that you can find the field from one source, the separately, like an independent problem, the field from the other source, like an independent problem, and then you sum the two fields. So in this particular case, it would mean that I could take this, copy, and then paste it again. And then what I could do is, in the first one, eliminate the second source. In the first one, eliminate the first. Solve each one of these problems separately. Find the two fields, E1 and E2, and then say that the total field equals to E1 and E2. What are the two conditions for superposition? Conditions to apply superposition. There are two important conditions. Number one, independent sources, which we already said. What is number two? Who can tell me? When can we apply superposition? We can apply superposition. Yes, go ahead. Somebody was ready.
Oh, I was going to say you can apply it whenever it's acting towards the same point.
Of course, it has to be at the same point, all right, to be able to do that. Because if it's at two separate points, of course, you cannot superimpose that. So we're talking about the same point. But there is one other thing, that the relationship between the source and the field has to be linear. So linear relation between E and Q. Do we have a linear relation between E and Q? What do you think? It's linear. Do you see that here? The E or D depends on Q only. When would it be non-linear? If Q was in a power or it was a square root of something. If Q was Q squared instead of Q, or it was Q equals square root of 2, square root of Q instead of Q, those would be non-linear relations, okay? You remember that?
Wouldn't it also be unlinear if one of the charges was moving towards the other one?
Yeah, that means that will be, they would not be independent, but there will be a relationship between the two. All right, so if the two charges are not related in any way, then, and if the relationship between the field and every charge is linear, then you can apply superposition. Why is that important? I'll tell you one very important thing that everybody in this class and later specifically makes a mistake. You know where it is? In this relationship. Why is that? The field is linearly related to the source. So voltage, for example, as we will see later, is linearly related to a current, all right? Voltage is IR, Ohm's law. But power is not linearly related to the current. Power in circuits is VI. So voltage, so let's see here. Let's assume that voltage is the field, source is the current. According to Ohm's law, you have that. What happens if you look at power? How is that related to current? Which of the two you can, on which of the two you can apply superposition? If this is your source, if this is the result of the source. Only the voltage, all right? Only you can superimpose voltages and for that matter fields, but you cannot superimpose powers. Do you remember that? Or at least if you have not heard this before in that context, please remember it now. A lot of students, even graduate students, make this mistake. You can only superimpose voltages. You can only superimpose fields, but you cannot superimpose their powers, all right? Because that violates the linear relation condition. Okay, now that I have mentioned that, and that is important, so I will also use this here. I would like to say normally the way we solve the problem is to do this. We separate the first charge, separate the second, solve for the first charge, solve for the second, and then we superimpose. So that's what I'm doing here. I used this equation that we found before. You remember this equation we found just before? I used this to find the electric field E1 at point O from charge Q1. And I calculated R1 as a vector, all right? And R1 is here. I calculated R1 as a vector. How did I calculate R1 as a vector? What did I do? Can somebody describe to me? I know the point at Q1 and I know O. So how did I find vector R1?
The difference between the origin and this point.
Exactly. So the difference, you remember that a vector, if you have a vector here like this, let me use a different color and then I will erase it. I will do it now. If you have a vector AB, and you know all of these, bx, by, and bz, and you know all of these, ax, ay, and az, and these are all the coordinates, then vector ab has an x component, which is bx minus ax, all right? A y component, which is by minus ay, and a z component, which is bz minus az. You remember that? That's what I've done to find vector r1. And that's what I did to find vector r2. And this is up here. Okay. And then I go and find the magnitude of r1. And how do we find the magnitude of r1? Can somebody tell me?
Square root of all the components.
Yes, it's the square root of the x component of r1 square plus the y component square plus the z component square. Okay? It's the square root of those three squared. And then, so that gives me 18, because here it's 9, 3 square is 9, plus 3 square is 9, 9 plus 9 gives me 18, and that's what it is. And then here is 2 square is 4, 3 square is 9, 13. So I found those two. And then since I have this one and this one, what I replace it here. And that's what I find this one. And in the same way, I now look at charge Q2. I use the same formula for that charge, and I find the field that is coming from this charge. And then what do? I superimpose. That's where I do the superposition. And I sum up the x with x component, the y with y, the z with z, as I do superposition. And that's therefore what I find here. All right. So practically, I used the superposition theorem, which is this one here. And there, I'm doing that because I'm going to copy this. I use the superposition theorem, and then I solve the problem. And then if I want to do a little more processing, I do this here. And what do I see? Do you see what I've done here? Not only I worry at the end about the correct value because I replace all of the coefficients, but I also worry about the units. What do you see that when I apply the units here, what is happening is that depending on the units that I have given you, you will have powers of 10, which at the end, the units, if you incorporate them, will change you the value. So a lot of times, the mistake that we do, another common mistake, is that we do all of the calculations, we do nothing with the units. And sometimes, if, for example, I'm giving you all of the dimensions here, all of these, if all of these, which are dimensions, all right, in front of the coordinate, it's dimensions on the XYZ system. If I give you that in meters, like I say here, did you see what I said in the beginning of the problem? All the dimensions are in meters. This is extremely important because then when I have to go back, I have to implement all of these dimensions, and I have also to change millicoulombs to coulombs, which is 10 to minus 3 coulombs. And then the meters, you can leave them if you wish. I left them, I made them millimeters. But it is coulombs per farad that gives you volts. So you always measure the electric field in volts per meter, millimeter, centimeter, millimeter, whatever. It's volts per length, per length. So you have to pay attention to units the same amount you pay attention to E, because if you give me an expression without units and you put the wrong units, say somebody would come here and put volts per meter with the same data, then it's a wrong result. And it's wrong result by many orders of magnitude. It's not just say, oh, you know, I made my units wrong. No, you did not have the units wrong. You had the whole result wrong. That's what happens with units. So please pay attention. Any questions so far before we go to another problem?
Professor,
Yes.
what did we calculate the epsilon naught constant to be in that example? Sorry, I didn't
Yes.
see that.
Yes, the epsilon naught constant. See, I incorporated without saying it. So let me do this here for a moment so I can add it. I'll take this a little lower. And here, I have incorporated here, but I will write it explicitly. You see this one? I replaced this by that. So what I used is that epsilon naught is 10 to minus 9, one way of doing it, 36 pi, and it's farads per meter, or you can write it as 8.85, let me see the rest, 854, 10 to minus 12, and it's farads per meter. And why did I use the divided by 36 pi? Because I had the 4 pi there. So pi is not, it's, you know, it's not an exact number. So I was able to cancel the pi easily. And then 36, it made me 9. That's why I used one over the other. But you can use either of those too.
But wouldn't the spherical densities of the two charges be different, being that they're of two different values and that therefore the epsilon naughts be different?
No, the epsilon naught only depends on the medium. And if the charges are both in free space, epsilon naught is going to be the same. Now, since I'm looking at the field at the same point, the only real possibility, if there is a difference in the medium, is that the point that I'm looking at is going to be in one medium. All right, the point cannot have half of one medium, half of the other, unless I'm on an interface, and that's a more difficult problem. All right, we solve it differently if it is on a dielectric interface. But in all of the problems we'll solve, the field, the one point here, you have one point in free space, is going to be, at least in the vicinity of that, is going to be the same medium. You may have one point here in free space, and the other point may be embedded in a dielectric. That is possible. But at the point where you apply this relationship, epsilon naught will have to be the same. Epsilon naught depends on the medium only, not on the source, not on the charge.
Okay, I get it. Thank you.
Okay, the value of the charges comes here. You see? Oops. The value of the charges comes here. And I have incorporated those differently. So one is 5, the other is 2. Okay? Any other questions? So we move now to another problem. so we look at the problem in 2 dimensions, in 3 dimensions, excuse me. Why was it in 3 dimensions? Because you have 2 charges here too. And they are separated in 3D, each one of them in 3D, X, Y, and Z. And the problem is a 3D problem. All problems in reality are 3D problem. However, there are some problems whose specific charge distribution or specific conditions, all right, can reduce its complexity and can reduce its dimensionality. So since real life is 3D in space, everything is 3D. But some cases in electromagnetics and many other problems, as a matter of fact, specific conditions about the source will allow us to simplify the problem by reducing the dimensionality. And you remember when I told you that the key thing in engineering mostly, in many sciences, math and physics as well, but I would say engineering, the key thing in engineering is to reduce the complexity of the problem. The person who knows under what correct conditions you can reduce the complexity to a lower complexity and then even a lower one is a winner, because this is the person who can really solve the problem and understand the physics. All right. Of course, nowadays, the old days, you had to do that to be able to do anything useful. Today, you can say, well, I'm going to go to MATLAB and put everything. Well, no, because if you go to MATLAB and do everything, you're going to miss the opportunity to develop what we say intuition. How are you going to develop intuition about how the field varies depending on the source that produces it? And so you have that here in your mind as you are thinking about designing something, because designing is a synthesis. In a synthesis problem, you have to take all of this information, synthesize it to find a solution. That's the design. It's a more complex than analysis, obviously. How are you going to develop intuition to help you how to synthesize things if you always go to MATLAB? You're not going to do that, all right? So we still have to learn how to reduce dimensionality and complexity. So now that is in a first example. Let's assume, and I'm sure we're going to continue next time, but I would like to show you here before I go to the solution. We have a source that is very long. It's so long, like it's a line charge. It's so long, this line charge, that we can, we are here, we are an observer. So we are this. We are an observer P. And that's a charge that extends from minus infinity to plus infinity. All right, so here's minus infinity to plus infinity. And of course, it's like the same. I mean, the charge here, Q, in reality, if this is the Z direction, charge Q of Z is a constant. All right, if you go on this line, the charge Q is a constant. Now, if I take a cross section of this, let's assume that I take this cross section and I look at that cross section. So what am I going to see? I'm going to see the center. All right. And then I'm going to see this circle. And on this circle, I'm going to see the observer somewhere here, say. Do you agree with me? That's the cross section. Cross section. Now, if I do the cross section at one point Z, and then, so say for this here case is Z equals Z1. And then I do the same thing on another cross section. So I move it, copy, and paste here. And then this is Z equals Z2, and I still put myself in the same location relative to the center of the cross section, what do you tell me about these two cross sections? That they are identical. Do you agree?
Yes.
Okay, if they are identical, and of course within my limitations for graphics, if they are identical, then what do we say that we have? We have an infinite source, and because of the conditions of the problem, because Z is independent of Z, every cross section is the same wherever you are, then we say that that reduces to a two-dimensional problem, which is this one. So the 3D here, 3D problem becomes a 2D problem where we do not have Z. So no Z dependence. What does that mean? That the cylindrical system here becomes a polar system there. All right, in such a reduction, the cylindrical coordinate system reduces into a polar system. Okay, so that is what is interesting here, obviously. So first, number one, that's very important. Number two, let's go back to this. You say here, okay, you did that, but why did you consider then this kind of volume? Because I wanted to apply the divergence theorem. And at this point, we have developed the divergence theorem to apply between in a three-dimensional space. And I did not want to change it into a 2D because mathematically it's going to be intense. So I said, okay, let's recognize, first of all, what I said here, that the cross section is identical wherever I am. All right. And therefore, because the cross section is identical wherever I am, I can take one cross section only, and I can create a small cylinder, finite, which has a thickness of d sub z. You see here? I said because of that, then I can create a teeny cylinder that is like a coin, practically. It's like the coin, this is like a quarter. It has a very big cross section, like the flat side. The two faces of the coin are the cross sections, and the thickness of the coin is the thickness of the cylinder, d sub z. And then now, since I have kept my 3D, but I have also considered that everything is identical in terms of the cross sections. So what I do is I apply here the divergence theorem. So my volume here is the volume of this coin, if you like, or of this thin cylinder. And the surface of this thin cylinder is made out of a cylindrical surface, which is has a thickness of d sub z, so a teeny thickness, and of the two surfaces, the upper surface, the two faces, if you like, the upper face and the lower. And each of the two surfaces have opposite directions, because you remember what we said in the surface, the direction of the surface is always the normal vector outwards. So N1 here is the normal vector to the upper surface outwards of the volume, and then 2 is the normal face outwards. Okay. Because these two directions of the surface are identical but have opposite directions, and because on these two surfaces the field is identical, since we talked about this before, then whatever surface integral I have on the upper surface, that's rho that you see. I had a question. So whatever you see on the surface is, on the upper surface, whatever integral you get is going to be canceled by the integral on the lower surface, because just the direction of the two surfaces is different, but the two surfaces are identical in whatever happens there. So practically, the only integral that remains is the integral of the thin area around, if you have the coin, the area around the coin, which in fact, the area of that is just this here. This is rho. All of these things that you see, it's rho. When I do P for me, let me see how I do the P. So you know, I do the P like this, usually, all right, the lowercase p. When you see me doing something like that, or with an equal tail, with a straight tail, that's rho, especially if you are in a cylindrical coordinate system, because I have seen some questions. Okay, so practically, this is the, what is the surface of this perimeter here? It is the perimeter of the circle, which is 2 pi rho, times the thickness, dz, here. So this is the area around it. And what is the vector d, which is according to that here, which is the inner product of the vector with the surface, should be, since the direction of the surface is this one, it should be d sub rho, which is the radial coordinate of d in that cylindrical system. And therefore, from here, we get this expression for d. The d in this problem has only one component, the radial component, and is given by this expression, which then reduces to this if I take into account the unit vector representation. So I would like you to look at this. We are going to continue with that next time, and then we'll solve some other problems. All right, but I wanted to show you how now we take the divergence theorem on Gauss's law, and we try to calculate more complicated problems. It's easier to do it like that instead of starting with Coulomb's law and try to integrate. All right. Okay. Any questions so far? Yes, I will post the notes. I said I will post the notes after the lecture. Always, I do that. Not immediately, but within the same day, I will do it. Okay. Any questions?
Professor?
Yes.
Can you explain the two normal vectors that are going parallel to the infinite charge?
Yes.
What properties did you say those had?
The two normal vectors are in opposite directions. All right, because you remember what we said, if we have a volume, any volume, I will draw here a volume. The vector of the surface is a vector. The direction of the surface is always normal to the surface and outwards. Now, if our volume is not like round like this, but it's like this, let's assume you have a coin and you're looking at the volume of the coin. All right, that's a quarter. You look at the volume of the quarter. Now this is the quarter, I drew it here. And then these are the three surfaces. The coin has three surfaces, the upper face, the lower face, and the rim, okay? So the rim, which is this one, has this direction, always outwards, and you go around, it looks like, it goes around like this, the direction on the rim. The upper surface has this direction. The lower surface has this direction. The upper surface and the lower surface have opposite directions. And because the field in there is identical in the upper and the lower surface, but the directions of the surfaces are opposite, then the integrals on these surfaces will be opposite to each other. So they cancel out. And that's why we only have the integral on the rim, on the surface of the rim. Okay, is that clear?
Oh, okay. I guess then if the purpose of those normal vectors parallel to the charge is to serve to model the
surface
the
as a
flow
vector.
coming from the ends of the charge
yes.
wherever they are, then why make them infinite in the first place? Why not just make it a finite line charge?
Oh, the charge. We consider it infinite because if you had it finite, that you had to integrate that from minus infinity to plus infinity. And then you would have, I'll show you why. Because if I had, this is a very good question, as a matter of fact, that you asked me. If I had, say, this charge here, and I will say, okay, this is a section of a charge, this is dq, all right? That's what you're telling me, isn't it? And then for this dq, it will create a dE field that is going to be A sub rho dq r over 2 pi epsilon naught r squared. Okay? And then I would have to find the total field. How would I find the total field in that? I would have to integrate the total field. You have to integrate from minus infinity to plus infinity dE. And then I would have to integrate. You can do the same. You can say, okay, so you will have an infinite. See, the problem then, you will have to integrate that from minus infinity to plus infinity. And mathematically, you will come out with an infinite number. So then you will have to go from the infinite number to the line, to this one, which is electric field, but per in a two-dimensional problem, all right? So it's Q sub L, which is the density, the line density, and that is going to be voltage per meters, but primarily because it's going to be a line density. If you put the units, you will see what's happening. But that's how I did it, because for me it's easier to do this instead of doing that. But you could, I think, in the book also addresses this problem for a finite cylinder from Coulomb's law.
Okay, I'll take a look at the book then. Thank you.
Yeah, take a look at the book, and you know what I suggest, if you have any time, try to do it yourself using Coulomb's law. So you consider a dq, and because it's like so small, you consider it as a point charge. You use Coulomb's law to find the field from a point charge, and then you integrate. See what you get.
Okay, thank you.
You're welcome. Any other questions?
Professor, I had a question about quiz 3 on Top Hat.
Yes.
So for the vector E, there seems to be a little symbol at the end. I was just wondering if you could clarify that.
Okay, yes. In fact, let me do that. 1 second. Let me go to this, all right?
Okay.
Sorry. Yes, I have to go to this one. Go to this one. Yes, here we go.
So I was just wondering what the vertical line was after the X hat for E.
Nothing.
Okay.
I think, to tell you the truth, that most probably I took this You know what I do a number of times because I cannot enter these symbols into Top Hat. I type them on Word, and then I do a capture of that portion of the Word file, and then I think that was the line where, you know, the prompt was to line. There was a line, you know, the line.
I figured it was just the cursor. Thank you for
Yeah, it's a
clarifying.
cursor. Yeah. Sorry.
I have a question for quiz 3 as well.
Yes.
For number 4, is it supposed to be -9 x hat? Is the x hat supposed to be there, or is it just supposed to be x?
No, I'm just giving you that might be wrong. Okay, what I'm saying? If somebody gives you this, say, I'm giving you that, you don't know whether you have to find the one that is written correctly.
Okay, I was just making sure. Thank you.
Yeah. So take it the way exactly it looks and figure out which one is the correct one that is written correctly. Any other questions?
This quiz is still due before class on Monday. I didn't hear your response.